Products and quotients of functions really is exactly what you would expect. And there are very few tricks to it. Like there's nothing really to worry about or think about. Like you could kind of teach this to yourself. Okay, so we've got two graphs, x plus 3 and negative x squared plus 3x. The graphs are given, as you can see in the graph, and it wants us to graph the product of the two functions. So again, we can write this in two different ways, like that, or actually as the product of two functions. Okay, so we're going to look a little bit at the actual values. So given these x values, find the y values. You can start doing that. This one's f at x, and this one's g. And then we'll use the product of those values to find the product function. When we added functions on Friday, we had that visual, that demo of what it looks like to actually add, and it's easy to visualize. It would be the same with product, except you're multiplying, which is maybe a little bit harder to visualize, but piece by piece, when we are done graphing and then you think about it and look at it, piece by piece, I think you can make sense of what's happening, and it's a worthwhile exercise to go through. And then the second example, which is an application, that's where this stuff really shines. There's a lot of applications. It's where you start to see the true power of modeling real world things with math, right? Real world circumstances. When we can start to combine functions, it really opens up a lot of possibilities. Okay, so let's go ahead. So the value of f at x at negative 3 is 1, 2, 3 is 0. G's not on here, but nevertheless, when I could figure it out algebraically, but I'm not going to bother right now. Just save a bit of time. The product will be 0, right? So remember when we did rational functions and we talked about looking for zeros on the bottom, which gives you on the bottom of a fraction gives you an asymptote, and zeros on the top gives you an intercept, and all those little key ideas. That's going to be a part of today and tomorrow as well, as thinking about like where are the important points of the graph? Where would there be asymptotes? Where would there be intercepts? That's going to help us understand the nature very well. Okay, so at negative 2, I've got a 1. G at x is negative 10. 1 times negative 10 is negative 10. Okay, so you can go ahead and continue. I won't do all of these for you. You can do them. Okay, then we're just going to go ahead and plot those points. what kind of a function is this going to be? Sam? Periodic? Why would you say that? Yes, it does. Anybody else have anything to add to that? Think algebraically about what we're doing. Anybody have any thoughts on this? I'll give you another hint. So remember, like when we did, so this is a product of two functions. We're going to talk briefly about quotients of two functions as well. But we've already done quotients of two functions, special kinds of functions, polynomial functions, when we did rational functions. It was the same thing. And how did we, the first day, I remember we talked about graphing, and what did we do? We did things like, okay, so if I'm multiplying these two functions, this is going into the negatives, getting bigger and bigger and bigger and bigger and bigger negative. And this is going into the negatives, getting bigger and bigger and bigger and bigger and bigger negative. Multiplying two negative numbers together gives me a positive. And if both numbers are getting bigger, the product will continue to get bigger, right? If it's a quotient, when one gets big, if they both get big, or one gets small and one gets big, it depends on if it's a numerator denominator. If the denominator is getting big, 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 the whole thing's getting small, 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 small. But in this case, it's just a product. If they're both getting bigger, the product is getting bigger. They're both negative. They will both forever be negative. So what's the end behavior of the resulting function, the product of the two functions? It's going to go off this direction, right? As x gets smaller and smaller and smaller negative, both f and g functions are getting negative, will stay negative, getting bigger negative, so their product will get bigger positive. What about over here? This one's getting bigger, 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 bigger positive. This one's getting bigger, bigger, bigger negative. I multiply them together. What kind of a number am I getting? So what's the end behavior, Chad? Yeah, and it's going to just get bigger, bigger. So the end behavior this way. See what I mean by thinking about like important properties and the nature of its properties, like end behavior, those kinds of things. The next question says determine f at x algebraically. Maybe we should do that first to help us think about this. So f is x plus 3, g is negative x squared plus 3x. Remember at the end of the lesson on Friday, there was that example that was like a silly example. Find the addition of these two, and you just wrote it, and then you were done because you can't simplify any further. Often that happens, but in this case, we can simplify further, right? So x times x is negative x cubed plus 3x squared minus 3x squared plus 9x. Those actually go away, and I get negative x cubed plus 9x. I don't know, that looks right. I think that's right. What kind of graph is it? Vivian? Cubic. It's cubic. Leading coefficient? Negative. What does that tell us about end behavior? We can factor this. So it's going to be, let's say, negative x and then x squared minus 9. We don't have to do this, but this is nice review for the exam. Remember we talked about polynomial functions factoring. What does the factored form tell us? About the intercepts. The order of the intercept tells us the nature of the intercept. Remember, you can have a linear pass-through, or you could have a turning point. Like if there was a squared on one of those, right? How many intercepts, all that good stuff. So I should have an intercept at +3, an intercept at -3, and an intercept at 0. So there is a symmetry going on. I think that's kind of what Sam was talking about. Okay, so let's see if we can draw this. Ooh. I don't actually know. Whoa. Kind of tricky, but. I don't know. Well, I could figure out where the maximums are possibly by thinking about the product. Like I could, like what's, like is there a, where's the local maximum? That point may not be a local maximum, right? Like I think a lot of people would put the turning point there, but we don't actually know that. You might be able to think about it if you think about the product of this and this. This keeps getting bigger until I get to there, but this keeps getting bigger over and over. So I don't know, it's a little bit tricky. Anyway, okay, there we go. That just helps us visualize a little bit what's actually happening when you take the product of two functions. Just like when we're adding two functions, you're literally taking the product of the y values. And so thinking about if this one's big but this one's small, what kind of a product does that give me? If they're both big but one's negative, what kind of a product does that give me? Those kinds of things, good ways to think about it. Okay, and then algebraically, in some cases, we can do it. And this is why this course is called Advanced Functions. Look at how much we know about functions and different kinds of functions in different forms. I can rearrange that cubic function, and I know a lot about it. It's end behavior, it's intercepts, all kinds of things. And then when we did all that rate of change stuff, thinking about local max and mins, that gives us something that continues on in calculus. Those of you that are taking calculus next semester, you talk more and more and more about finding local max and mins, that sort of thing, to help you also find more properties of these graphs. Okay, this is a really neat application. A pendulum swings back and forth and loses 10% of its amplitude with each swing. So the displacement of the pendulum, like going back and forth, how far it's going to the left and to the right from some zero, that would be where it would be at rest, I guess. That's what we mean by displacement. It's not like the height necessarily, it's like how far back and forth it's going. Can be modeled by the product of a sine function, because it's got that periodic nature of going back and forth. But the sine function always goes up to 1 and then down to -1 and then back up to -1 and down to -1. If the pendulum loses some of its amplitude with each swing, the amplitude of the periodic function will decrease constantly, right? But every time it comes back up to that maximum height, it'll be a little bit smaller. So it starts here, but by the end of it, oh, this looks like it's got the wrong graph on it. Oh, no, that's right. Yeah, sorry. But by the end of it, it's not going to be up hitting that top. Those are the two base functions, sorry. Right. We have to add the new function on there. Okay, so the amplitude is not going to be 2 every single time. It's losing its amplitude. It doesn't have as big a displacement. And that's happening like in an exponential decay pattern, right? So we have the graph here of 2 sine pi x. Another little bit of review. So the amplitude is going to be 2. So 2 to -2. And what does the pi x tell us? That tells us something about the period of the graph. So we can figure out the period. But you can see that it's 2, because that's when one period takes place. Otherwise, it's a sine function. And then here's 0.9 to the x is the green curve. So now let's find the product of those two. But we're not going to do a table of values here. We'll just kind of think about it and look at it. So here's what I'm going to do. This is 2. This is just under 1. This line here is 1. So the green curve is just under 1. 2 times just under 1 will give me what? Approximately. Yeah, but should we put a point at 2, or where could we be a bit more accurate? Brandon? Just under 2, right? Because it will be a little bit less than 2, so we can put something just under 2. When I multiply by 0, I get 0. 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 That's something you've probably learned about pendulums, no matter, like, it swings back to the 0 line at the same time, right? The time of the amplitude is the same, but it's just the size of the amplitude changes. So it keeps swinging back at the same time. And then look at this. This is less, like it's under 1 by more than the first time. So if I have a very small distance here, it'll be a slightly bigger distance here. And then same thing, it's more under 1 here. So even more, and then even more. And when will I get, let's see if we can find another point. Here's a good one. Right about there, it looks like we're at a half. So 2 times a half is 1. So at that point, we should be at 1. And then we'll be below 1 here. And even further, and even further. And so on and so on and so on. So it's a sine curve that's getting increasingly smaller and smaller and smaller over time. Any questions about that? The more math we're able to do, like computationally, that we have the skills to actually do the mechanics of the math, the more complicated and just the more real world experiences we can model, and model them more accurately. We might have modeled this in a previous grade, doing some kind of activity around something like this, and not thought about how the amplitude is decreasing every time. So there's, yeah. Actually, this is, no, I must have been goofing around with this thing. Oh. Maybe it's this one. Nope. I'll figure it out and see if we can look at it. And this doesn't actually ask us to do any questions, so that's that. For quotients of functions, it's the same thing. You're just dividing. There's very few questions. Take a look. There's only 3 questions in the textbook for that section of the chapter. And you only have to do B, C, and D for 1 and 2, and then question 3, which is pretty easy. But you'll notice that quotients of functions is similar in some ways to that rational function stuff we did. When you have a 0 in the denominator, a 0 on the bottom of a fraction, that gives you an asymptote. So that's going to be a big part of that quotients section.